Yeah, I think now we are live on YouTube as well. Okay. So let me go back here. I will share my screen just for a few minutes. Today is our last webinar of the year. And we will resume next year. Before I introduce Professor Kosterlitz, actually, Professor Enzo Granato will do that. Let me just announce our next webinar. After we have a month vacation on January, we will resume on February, February 8th, and we are going to have Professor José Arroyos from USP, and he's going to talk about frustrated magnetism from disordered to ordered and back to disorder. Today we have the great pleasure and honor to have Professor John Michael Kosterlitz, and I kindly asked Professor Enzo Granato, a longtime collaborator of his, to introduce him. So please, Enzo, you can start your introduction.
Hi, everyone. It's a great pleasure and honor to introduce you, Professor John Michael Kosterlitz, for Brown University, for this web seminar in condensed matter physics. He received his PhD from Oxford University in 1969 and was already on the faculty of Birmingham University, UK, before joining the Department of Physics at Brown University in 1982. Professor Mike Kosterlitz doesn't need much of an introduction, of course. His name is well known and already appears in many modern textbooks of condensed matter and statistical physics associated with the so-called KT transition, which is just an abbreviation for Kosterlitz-Talos phase transition, that occurs everywhere in two-dimensional systems with a continuous symmetry. And the famous Kosterlitz renormalization group equation describing the critical behavior of the two-dimensional XY model mediated by topological effect. His work has far-reaching applications for two-dimensional systems, ranging from superconductivity, superfluidity, to melting growth of crystals and related one-dimensional quantum systems. Of course, it should be enough to say that he was awarded the Nobel Prize in Physics in 2016, together with David Talos and Duncan Haldane, for his groundbreaking work on topological defects and topological phase transition. Today, we will have the opportunity of hearing his talk precisely on this subject. He has also been receiving many other important prizes in physics, such as the Maxwell Medal and the Onsager Prize, and he has also worked in a variety of other interesting problems in physics, such as glassy systems in general, surface growth, phase field modeling, and more recently on pattern selection by stochastic noise, about which he already gave a web seminar to the Brazilian audience very recently. Now, I would like to take this opportunity to say a few words about Mike Kosterlitz's Brazilian connections. I had the privilege of being his second PhD student at Brown University, working on superconducting arrays. But before me, Mike also co-supervised Jairo de Almeida from University of Pernambuco, together with David Talos on spin glass systems at Birmingham University. He also worked with Raimundo Costa Filho from University of Ceará on pattern selection problems when he was a visiting professor at Brown University. Mike Kosterlitz has been visiting Brazil from time to time since 1988. His last visit was in the celebrated year of 2016, when he was visiting INPE, Instituto Nacional de Pesquisas Espaciais, just a couple of months before the announcement of his Nobel Prize in Physics. With this, I stop and give more time to the speaker. Let's welcome Professor Mike Kosterlitz.
Thank you, Enzo. Professor Kosterlitz, now you can share your screen.
Okay.
And let me just say that, as usual, if you want to make a question, if you want to ask a question, you can either raise your hand using Zoom, or you can write the question in the chat, or you can ask questions at YouTube chat as well, and Professor Angela Clautal will take care of that. Thank you, Professor Kosterlitz. The screen is yours.
Thank you. Okay, so I don't really know what I'm doing here. Can you see?
Okay, we can see your screen. It's perfect. Yeah.
Okay. Okay, great. So let me start then, and this is a talk on the subject for which I won the Nobel Prize with, along with David Thouless, called Topological Defects and Phase Transitions in Two Dimensions, with an alternative title, A Random Walk Through Physics to a Nobel Prize. Now, the alternative title was actually chosen with some care because it really was a random walk through physics. You know, I had no idea what I was doing. I had no idea what the problem I was working on was had any importance whatsoever, except as an entertaining bit of physics. But it's turned out to be more important than I thought. So let's see if I can there we go. Let's go to the first slide. Oh yeah, so we sort of thought about this problem, and you know, as I said, we solved a little toy, what I thought was a little toy problem, and we published a few papers. This is when I was a postdoc at Birmingham on it. Two with David and one by myself. And, you know, they're published in a relatively, you know, not a terribly prestigious journal, but so, as I say, the work eventually got quite well known and had a lot of citations eventually. Actually, for the first 5 or 6 years after we did our work, I don't think we had a single citation because basically nobody really understood what we'd done, and I remember having all sorts of comments, you know, like, what on earth do you think you were doing? And I tried to explain it, but it took some time before it was appreciated. It could be that we solved the problem in the most difficult way known to humankind, which often happens when somebody does a problem for the first time. But it wasn't for a few years. It was only a few years later that David Nelson and Bert Halperin got interested in the problem, and they redid our derivation, but in a much simpler and more sort of obvious method. And that was the method eventually caught on and made things, the whole thing usable. Now, so the problem that David and I were interested in was really a conflict between theory and experiment. You see, in the early 1970s, there was a theory rigorous theory, which said there was no long-range order in a two-dimensional system with continuous symmetry. Basically, what that meant was that, you know, if you think in terms of a magnet, that if you lower the temperature of this system with a magnet with a continuous symmetry, that you never got a spontaneous magnetization. You know, at any non-zero temperature, you could not have a spontaneous magnetization. And so most people in the physics community at the time then assumed that there was no phase transition. The system didn't have a phase transition because the guru Lev Landau had told us that the difference between a high temperature disordered phase and a low temperature phase was that in the low temperature phase there was long range order. Now that was not a rigorous statement. It was just a statement made by the guru, and everybody took it as true. Now, this particular system we were interested in, which was the two-dimensional XY or planar rotor model, or a thin film of superfluid helium. Therefore, this system couldn't have any long-range order at any finite temperature, and therefore the theory said that there wasn't a phase transition. But then this experimental data came out. Actually, we looked at a preprint, but it was published in 1975. It was actually published in 1972, and it was a rather clever experiment. They took a resonant crystal, a certain resonant frequency, and they absorbed a thin layer of helium-4 onto this resonant crystal. Now, if you think about this for a moment, if the helium particles stuck to the crystal, and so when the crystal was vibrating or oscillating, the helium atoms would oscillate with the crystal. And therefore, their effect should be that they would simply increase the mass slightly of the resonant crystal, and therefore reduce the resonant frequency slightly. And so, if you did an experiment, what you should see is the resonant frequency as a function of the pressure of the gas, the helium gas, in equilibrium with the crystal, should be this straight line, because all the straight line means is that as you put some more helium on, as you increase the pressure of the helium, the extra helium will simply stick to the crystal and therefore increase the mass of the crystal, and the frequency would simply decrease, and the resonant frequency should follow the solid straight line. So the experiment was done by Chester, Yang, and Stevens. And when they did the experiment, of course, it started off not quite following the straight line, but fairly quickly, as they increased the amount of helium absorbed onto the surface of the crystal, the experimental points hit the expected straight line and followed it as the pressure of the gas was increased, exactly as one expected from a naive point of view. But then, suddenly, when some certain amount of helium had been absorbed from the surface of the crystal, the expected frequency and the measured frequency diverged. Suddenly the frequency the resonant frequency of the crystal remained higher than expected. And so and therefore this indicated there was something funny going on, because all this meant was that some fraction of the helium absorbed onto the surface of the crystal was decoupled from the crystal. In other words, the crystal was vibrating. This some fraction of the helium absorbed onto the surface simply decoupled from the crystal. And that's what the experimental data indicated. And so when David Thales and I looked at this data, we sort of asked the question, well, okay, what's going on here? And of course, being naive and simple-minded, we said, well, okay, the simplest thing that could happen is that some fraction of the fluid, absorbed in the surface of the crystal was now superfluid and was decoupled from the crystal. However, remember that this would contradict the existing theory, which said, as I said, there was no long-range order and therefore no phase transition. So therefore, there could be no distinct low-temperature phase. That's what theory said. But this experimental data clearly said, look, there is a phase transition because at some particular coverage, some of the fluid then decouples from the crystal substrate and doesn't move with the crystal. And so what we said was that the simplest explanation for this is that the fluid, this thin fluid film, had gone superfluid, despite what the existing theory said. Because, I mean, and so the next thing we had to do was to cook up some explanation of how come a two-dimensional film, I mean, this film was really thin. It's only a few atomic layers thick. You know, so we had to cook up some model of this of the film, which had a phase transition to super. When you made the temperature low enough or the coverage high enough, that the fluid went superfluid. And so then we started asking the question, look, so let me go to the next slide. Okay, so then there was a more general question of what happens in two-dimensional systems. Here's and the ideal two-dimensional systems to think about are magnets. I mean, for example, you could have the individual atomic magnets, or the spins, could have any number of components. If you have one component, it would be an Ising system. Two components, it would be an XY system, or equivalently, this would describe a superfluid film. And if you had three components, it would be a Heisenberg model, and so on and so forth. And so the question was, what was known about such systems? And what was known about them was that if you had a one-component spin, an Ising model, two-dimensional Ising model, this is well known to have a phase transition. Due to Onsager solved this problem back in the mid-1940s. Then, if you have two spin components, you could define the order parameter as the x component of the spin plus I times the y component of the spin. And if the spin length is fixed, this could be written as an amplitude, just a spin magnitude, times e to the I theta, where theta is the phase of that spin. So in other words, there was this so-called order parameter, which can be written as mod psi e to the I theta. This is, of course, invariant when theta is changed by any multiple of 2 pi, because if the phase changes by 2 pi, the order parameter gets back to what it started with. And so, but you see, this allows for vortices, because if you say that you're walking around a point, where the order, where the order parameter has gone to 0, some singular, if you like, then what this would mean is that the phase would change by 2 pi, say a multiple of 2 pi, and if you convert this into the language about superfluidity, this means there's a vortex in other words, what's happened, you've walked around a vortex. And so the topology of the system is, if I integrate the phase angle around some closed contour, this has to be an integer multiple of 2 pi. So then, so this problem became interesting on its own because these vortex-like excitations are the only excitation that could reduce the magnetization from some non-zero value. And so if we just say, take an isolated vortex, in a system of size L, the energy of this vortex is just proportional to the logarithm of the system size divided by the microscopic length or the lattice spacing or whatever. But the entropy of such a vortex is simply, the standard Boltzmann entropy. It's just proportional to Boltzmann's constant times the logarithm of the number of possible configurations of this vortex. And the number of configurations is very simple. It's simply the number of positions that the center of the vortex can take on. And so in a system of size L, this is just the number of positions of this vortex center, just L squared or A squared, where A is just the size of the vortex, just the logarithm of the number of possible states. And so if you look at the free energy, which is just the energy minus temperature times entropy, this gives you something proportional to the exchange, this J, minus 2 kT, where K is Boltzmann's constant, T is the temperature. And so in other words, the energy, the free energy of an isolated vortex is infinitely, at low temperatures where the energy dominates, is infinitely goes to plus infinity logarithmically with the size of the system. And therefore, the probability of a vortex being produced by thermal fluctuations at low temperatures is essentially zero. It's a decay. On the other hand, at higher temperatures, the entropy also goes logarithmically with the system size. And therefore, the free energy will, as I said, at low temperatures will be logarithmically infinite, positive infinite, but at high enough temperatures, when the entropy dominates over the energy, the free energy will become negative and diverge logarithmically with system size. And this implies that the probability of an isolated vortex becomes 1. In other words, free vortices will be produced by thermal fluctuations. And the crossover point, if I look at the probability of an isolated vortex, this would go like the system size divided by the vortex size to the minus pi k minus 2, where k is just basically the exchange energy divided by temperature. And at low enough temperatures, the probability is essentially 0, because pi k minus 2 is positive. But at higher temperatures, pi k minus 2 is negative, and therefore the probability of a vortex will be large, or actually can't go bigger than 1. And so one expects something funny to happen when pi k, where k is just basically proportional to inversely proportional temperature, is about 2. Now, let's go to the next slide. So there should be, okay, so there should be a phase transition in the case where n is 2, or the superfluid, if you wish. However, then of course the next question is, what happens to the Heisenberg system, with an isotropic Heisenberg model with where the spin has got 3 components, so that the spin, the spin components can be defined in terms of 2 angles, the polar angle theta and the azimuthal angle phi. Now, if we look at if we believe that it's a topology of the system that drives a phase transition, and after all, in the XY case, or the planar rotor case, a vortex is a topological excitation. And so if we believe that the same sort of thing would happen for these topological excitations, or the important excitations, the phase transition, then what we should look at are the topological invariants. And for a 3-component spin, there is one topological invariant, which is written down in this slide. And this peculiar formula can be looked at as a mapping of the direction of the magnetization in space onto the surface of a unit sphere. And the invariant n measures the number of times space encloses the unit sphere. Now, in 2 dimensions, this invariant is of no consequence in statistical mechanics, because the energy barrier separating configurations with different values of this topological invariant n is of order unity. It's not infinite. Whereas for the vortex case, for 2-component spins, the energy barrier is basically of order the logarithm of the system size, and so it can separate 2 different topological sectors. Okay, so of course we haven't shown that there is a phase transition for a 2-component system, but if there is, then it does explain the difference. This argument explains the difference between a 3-component spin and a 2-component spin. Okay, now let's talk about the phase transition in a superfluid film. Now, as I said, the important excitations are vortices. And so here's a picture, here's my sketch of a vortex. And the blue blob in the middle just represents the core of a vortex. And this is a region where if we had a vortex, as we approach the core of the vortex, the fluid is circulating around a point, and the velocity of the fluid is then proportional to 1 over the distance from the center. And so close to the center of the vortex, the velocity of the superfluid is so high that locally the system cannot support superfluidity. So therefore the core, the center of the vortex, must be normal. Okay, and that costs you some energy, or free energy. So this is a picture of a vortex flow circulating in a clockwise direction. so if you call this flow pattern a vortex, an anti-vortex would the flow would be in the opposite direction. And the question is, so what? What do these vortices do? Now, the important point about the vortices is that, okay, just think about the following setup. Suppose we have a substrate. So we've got a film of superfluid on the substrate. And let's suppose this is flowing down the, from the top to the bottom with some constant velocity relative to the substrate, call it U sub S. Now, this is the superfluid velocity. Now, the difference between a normal fluid and a superfluid is that in a superfluid, the superfluid flow is at least metastable. And the question is now, then in the normal phase, the flow dissipates energy, and of course in the superfluid phase, the flow does not dissipate, but in the normal phase it does dissipate. Now the question is, what differentiates a superfluid from a normal fluid? Because we're starting from an ideal superfluid, and we asked the question, what excitations in the superfluid can dissipate the flow? And the answer is the only things that can dissipate the superflow are vortices. And you see what can happen. Imagine the following setup. Suppose we have a vortex pair, a vortex, call it with a plus, and an anti-vortex with a minus. And these are just two vortices with opposite circulations. And of course, as long as these vortex and anti-vortex are close together, such a configuration has got a finite free energy, and therefore these configurations will be present, in some concentration. Now, if we then impose a uniform superfluid flow relative to the vortices, or this vortex-anti-vortex pair, what will happen is one of the vortexes will tend to flow perpendicular to the flow, the uniform superflow, and let's suppose it goes to the right. And the anti-vortex will tend to go to the left, or vice versa. I'm not quite sure which. It doesn't matter. And you see, now, if the vortices are bound together, the superflow will be at least metastable. But let's suppose that at higher if you raise the temperature, this vortex-anti-vortex pair separates. The separation between them grows. And when they become, when the mean separation becomes sufficiently large, we can call these vortices free and, basically free to move. And so when we apply a uniform flow to some concentration of free unbound vortices, then these free vortices will simply flow because they're not bound together, and they will simply flow in such a direction as to dissipate the superflow. And so you can call such a phase a normal phase. And therefore the question is, what differentiates a superfluid from a normal fluid is that in a superfluid, the vortices will come in bound pairs. Okay, you know, the vortex and anti-vortex will, you know, in thermal equilibrium will basically be a finite distance, you know, finite distance apart. And then a normal fluid will be characterized by the same system, except the vortices and anti-vortex can be arbitrarily far apart and free to move, and the system will dissipate. So therefore, the physics of the superfluid is controlled by these vortices, because, as I said before, these vortices are the only thing that can dissipate the superflow and cause the superfluid to become normal. I mean, local excitations will have no, you know, have no effect. Okay, so, and so what we then did was we tried to cook up a theory of a set of interacting vortices. You know, do the statistical mechanics of a set of vortices and anti-vortices. And surprisingly enough, we managed to do this and formulate some sort of a theory. And so basically what the theory says is the following. One of the important correlation functions would be the momentum density correlation function. And that's what the top equations is. And so this can be written as a longitudinal part with a coefficient A of Q, depends only on the magnitude of Q, times Q alpha Q beta over Q squared, plus a transverse part, which is B of Q times delta alpha beta minus Q alpha Q beta over Q squared. And if the system is a pure superfluid, this correlation function will only have a longitudinal part. So in other words, the B will be 0 and A will be finite. Whereas in a standard isotropic fluid, then this correlation function is basically proportional to just delta alpha beta. In other words, we'd have A and B, the coefficients A and B will be equal. And so then, if you then do a little bit more analysis and ask the question, okay, we can characterize the system by a stiffness. You know, and the stiffness is related to the question of, suppose with the phase of the order parameter, there's two-component order parameter, so it can be written as magnitude times ETI theta. And the phase theta, suppose we keep the phase theta at one end of the system, say, fixed. And at the other side of the system, we call this the phase some different. And we ask the question, suppose we try to twist this phase. And it's like winding up a spring, okay? That if the spring is unbroken, there'll be a resistance to twisting the spring. And if this stiffness is non-zero, is finite, this corresponds to a superfluid. Now, if the spring breaks, so then there's no resistance to twisting the phase of one side of the system relative to the other side, this corresponds to a normal fluid. And so mathematically, this stiffness constant, this K sub R of T, which is in principle a renormalized stiffness, or if you like, it's in principle a measurable stiffness. This actually can be written in terms of the various physical constants like Planck's constant and the mass of the helium atom and the temperature and stuff like that. And what one calls the renormalized superfluid density, this rho sub S of R as a function of temperature. And that's the measured long distance superfluid density. It happens to have the mass, dimensions of mass per unit area. And this is equal to the limit as Q vanishes of the difference of A of Q and B of Q. And so basically, so therefore one can calculate this quantity in terms of the bare superfluid, the bare stiffness, or the quantity that appears in the Hamiltonian. Let's call that K sub naught. And so this measurable quantity is equal to K naught minus 4 pi squared K naught squared times the vortex correlation function divided by Q squared. Which in turn can be written as, by simply inverting the Fourier transform. This can be written as the vortex correlation function divided by Q squared, written as R squared times the vorticity at R, the correlation function of the vorticity at R times the vorticity at point 0. Now, the vortex correlation function can be actually written quite trivially. You see, there is we just assume that there is some fugacity, which call it Y naught, which is basically just the e to the minus the core energy divided by temperature. And so we can, to lowest order, these ends, these vorticities are plus, 0, plus or minus 1, plus or minus 2, etc. And so to lowest order, the average of the vorticity at R correlation function, vorticity at R times the vorticity at point 0 is just minus 2 y naught squared, where y naught, as I said, is the fugacity of the bare fugacity of the vortex, times the separation to the minus 2 pi k naught, plus a term, higher order in the fugacity. Now, if the fugacity is very small, let's suppose we can simply calculate this thing to lowest order in the fugacity. In other words, just keep the first term. Now, whether this approximation may or may not be good, but what we're doing is we're doing a perturbation expansion in the fugacity, vortex fugacity. And if the lowest order perturbation expansion works, that's good. And we don't have to worry about higher order terms. So then we can calculate write down a perturbation expansion for the actual renormalized stiffness constant. Actually, it's easiest to write it down in terms of the inverse stiffness constant. And this is just the bare stiffness constant, the inverse of the bare stiffness constant plus a term of order the fugacity squared. And the vortex correlation function is easily calculated to lowest order in Weiss in the fugacity as just this integral, which is a pretty trivial integral. Okay, now, this perturbation expansion can be converted into a renormalization group equation. And so what we introduce this parameter, the scaling parameter L, by calling the separation divided by the microscopic cutoff R over A, call that just e to the L. So L is just basically the logarithm of the separation. And one finds, after a little bit of calculation, well, actually, the first time this was done, it was not a little bit, it was a lot. All the physics can be subsumed into the two little equations at the bottom of this slide. dk to the -1 by dl is equal to 4 pi cubed y squared plus order y to the fourth, and dy by dl is equal to 2 minus pi k times y plus order y cubed. Now remember, we're assuming that this fugacity y is very small. So only going to keep the lowest order terms in the perturbation expansion. Okay, now when we do that, oops. We can summarize all the predictions of these fancy scaling or renormalization equations in these flows. And all the physics is contained in this picture. You see, what's happening here is the physical system is described by these two parameters, the initial value of k and the initial value of fugacity y. So call it k naught and y naught. And these two, so we plot what happens in terms of k and y. And the initial system, the starting physical system, will have some specific values of k and y, k naught and y naught. And they will be somewhere, let's say, on the right-hand side, some values on the right-hand side of this picture. But then these scaling equations, as we change the length scale, will cause these parameters to flow along one of the trajectories in the direction indicated by those arrows. And you can see that there are really two distinct regimes. There's a regime where the fugacity, as we increase the length scale, scales to 0. That's this bottom right-hand part. And then there's another regime where the fugacity eventually increases, gets larger and larger. Okay, now what does this mean? Remember, we talked about this before, because when the fugacity goes to 0, it means that we have an equivalent system with no vortices. And therefore, we can say that any system whose fugacity flows to 0 as the length scale increases must be in the ordered superfluid regime, because in the renormalized system there are no vortices and there's nothing to dissipate the superfluid flow, so it must be a superfluid, you know, in other words, that's the high temperature regime, the low temperature regime. On the other hand, if we change those parameters a little bit, we get to the regime where eventually the fugacity starts increasing and then keeps increasing. And this has to be interpreted as a high temperature phase. You know, where the, you know, this in the renormalized system, there are free vortices present, which can dissipate the flow. And this means that it's a normal system. You know, it's a dissipative system. Okay, now you may ask the question at this point, what if I got, you notice that there's a parameter called C on this graph. And this C is just the constant of integration. Right? When we integrate these equations, of course, you end up with a constant integration. And this constant integration I call C. And it turns out that this constant integration vanishes at the, you know, at the phase transition. And this corresponds to the straight line where the fugacity actually decreases eventually to 0. And this straight line separates the high temperature phase from the low temperature phase, and therefore this straight line must correspond to a system right at the critical temperature, or right at the phase transition. And these, then these. Again, now, when we first, you know, had these sketches floating about, and we were thinking about it, trying to understand what the hell the physics underlying these equations was, eventually we managed to, you know, sort it out, but that took a long time. Okay, so. Now, the crucial predictions of our theory. We'll come back to whether they've got anything to do with experiment in a moment. The first thing is, from the theory, the measured stiffness, which contains the measured renormalized superfluid density, is some case Kr, which depends on the initial parameters, the physical parameters, which I call K sub naught and Y sub naught. And this can be shown to be not change under this renormalization or this length rescaling. So this correlation function has the same value if the underlying variables are K naught, Y naught, or are K of L, Y of L, where K of L and Y of L are solutions of those renormalization group equations. And the most important prediction is in the last two lines of this curve. For example, the superfluid density, this, you know, H cross squared times rho S as a function of temperature divided by m squared KT. This is just the stiffness constant, this K. This is equal to the renormalized stiffness constant, you know, the physical and measured value. But what the renormalization group equations say is this is equal to the renormalized stiffness constant measured as a function of the coupling constant K at L equals infinity and the vortex fugacity at L equals infinity. And below TC, the vortex fugacity at L equals infinity is 0. And so this just becomes the value of the coupling constant at L equals infinity. And this follows directly from the picture on the previous slide. This is equal to 2 over pi plus a constant times the square root of the magnitude of the deviation from the critical temperature. You know, this T means Tc minus T. So it's the distance we are below the critical temperature. And what's more, at Tc, when this little t is 0, the renormalized superfluid density just below the critical temperature divided by the critical temperature is given in terms of 2 over pi times, you know, m squared times Boltzmann's constant divided by Planck's constant squared. And if we put and this is a known quantity, we put the numbers in, this is about 3.5 times 10 to the minus, I think I made a mistake, it should be 10 to the minus 9 grams per square centimeter per degree Kelvin. In other words, the theory is predicting that if we are just below Tc, the superfluid density divided by Tc is given by this number. And this number is an inescapable prediction of the theory. In other words, if this number is measured experimentally, the experiment if our theory is correct, this number had better be the value which I've written down here. Because if it comes out to some other value, it's plain wrong. The theory is wrong. And it's all back to the drawing board. So this is a real smoking gun prediction. And to our great pleasure, the experiment was actually done in a few years later by John Reppy and David Bishop at Cornell. And what they did, now unfortunately, this theoretical prediction, which I just talked about, it comes from equilibrium statistical mechanics, which means that the only correlation functions which are accessible to equilibrium statistical mechanics are zero frequency, you know, but, so in other words, what we've done is we have a formula for the renormalized superfluid density at zero frequency. But such a quantity is not measurable experimentally because the experiments have to be done with the frequency omega and the wave vector q, at least one of them non-zero. You can't do the static measurement because there's no way of measuring the superfluid, taking a piece of superfluid, and weighing it. You can't do that. And so it has to be done, you have to do a flow experiment. And the flow experiment that they did was use a torsional oscillator experiment. And this was very clever because they took a torsional, a torsional rod, and they wrapped a long strip of plastic mylar on this, like toilet paper. And so they absorbed helium onto the mylar, because after all, you need a fair amount of surface area to get a reasonable amount of superfluid helium to so that you can actually see the effect of this helium film on the resonant frequency of this torsional oscillator. And so the experimental results are basically these points and solid lines drawn as a best fit to these points. Our theory, the static theory, is unfortunately this discontinuous drop to zero of the superfluid density, which is well to the left of anything interesting in the actual experiment. Now, of course, the experiment was done, so the frequency of the torsional the torsional oscillator rod was, tens or hundreds of hertz. I can't remember. I think it was less than a kilohertz. But unfortunately, this is the characteristic frequency. This is very large compared to the characteristic frequency, because the characteristic frequency is related to vortex diffusion, and this is very small. It's it's probably a couple of hertz. So the characteristic frequency is a few hertz, whereas experiments done at these hundreds of hertz. So therefore, it's always done at the high frequency. And so what we get are two curves. There's a curve which simply goes basically to zero, and this is the real part of the correlation function, which basically measures the superfluid density, but as a function of frequency. And this does not do what the static superfluid density does, which falls discontinuously to zero, but it goes continuously to zero. And the other peak is the imaginary part of the correlation function, and this measures the dissipation, and it's it's very strongly peaked at where the superfluid density vanishes. So this is the experiment, and somehow it has to be compared with the theoretical prediction, which is well to the left of anything interesting happening in the experiment, because the comparison was actually made eventually by an extension of the static theory to dynamical theory. And this was done by Ambigaukar, Halperin, and Nelson. And so the fits to and this theory was based on the static theory, but the fits to the experiment was done using the dynamical theory. And so whether you say that fit is good or not is up to you. Okay, now the last thing I want to say is this is a this is basically the superfluid density against, this is the superfluid density just below TC as a function of TC. Now, of course, you ask the question, how do we change the critical temperature? How can you do that? Well, that's easy, because all you have to do is you just change the thickness of the film, of the helium film, because if you increase the thickness of the helium film, you increase the transition temperature. And so now the dots here are experimental points. There's some third sound measurements by Hallock, Michel, and Rudnick, and there are some points on this plot which are also due to the analysis of the experiment by Bishop and Nelson. And so what they got was this set of experimental points, which basically are scattered around, but they sort of follow a straightish line. The story goes that when these points were first plotted, which come from a number of different experiments, they didn't know about our theory. So they didn't have any. But you see, this straight line is sort of roughly what we'll do as a sort of best fit to these experimental points, this cluster of experimental points. But then somebody said, these guys in Britain, they have a theory, and they actually predict the ratio of the superfluid density to TC. And so basically what our theory does, it predicts the slope of the straight line. And if you superimpose the straight line with the slope predicted from our theory onto these experimental points, these are the results. The solid straight line is taken from theory, and the experimental, these are the experimental points. So this is the best confirmation of the theory, because I don't think anybody's ever cooked up an alternative theory which will can predict the slope of the straight line. And so this is taken as confirmation of the vortex theory for the two-dimensional superfluid films. Okay, now, there are other systems which also can be described by a similar theory. And of course, this is the melting of a two-dimensional crystal in 2 dimensions. And I sort of prepared some slides on this, but let's forget about that because we're running out of time. So let me just show this slide. Now, basically what happens is that the theory of the melting of a two-dimensional crystal is very similar to the theory of the destruction of superfluidity in 2 dimensions, and involves the theory of melting involves dislocations. And these dislocations are just exactly the topological singularity, the topological excitations of the two-dimensional crystal. So the theory in spirit is exactly the same as what I've described, but of course technically it's much more complicated because dislocations are much more complicated than vortices. But the idea is the same. And so the theoretical curve, so basically what the theory predicts is the value of the Young's modulus, because you've got 2 elastic constants in an isotropic system, and the particular combination that the theory talks about is precisely the Young's modulus. And so when you do an experiment, which is not easy, but it's been done, and you plot the Young's modulus against the inverse temperature, you get the red straight line, the red line, which plunges to a finite value at the critical temperature, the melting temperature. And the points with the large error bars are actual experimental points. Because the error bars are rather large, because these experiments are not easy. But I think one can say that, and the predictions is very similar to that of the vortices in that the Young's modulus, the measured Young's modulus, follows the line, and at the transition temperature, it is precisely 16 pi, which is about 50. And so it plunges down to the value of about 50 at the melting temperature. And so you can say that the comparison between theory and experiment for this melting problem is also pretty good. And so, oops. Well, and the last thing that it was applied to, you can apply the similar theory, is to cold atom problem, where you can actually see a transition and one can actually interpret this in terms of the so-called Kosterlitz theory. And the agreement between theory and experiment is not as good as for classical two-dimensional melting and superfluid onset, but it's not bad. Okay, so then let me conclude by saying that I would like to thank David Thowles, who unfortunately died a few years ago, for introducing me to this beautiful problem, David Nelson for collaborations in the discussions, John Reppy for many, many useful discussions, and the Nobel Committee for the recognition. And of course, I must thank my wife, Berit, for an incredible journey through life, taking us from Birmingham to Providence, to Torino to Providence, and finally, but not least, my children, Karen, Jonathan, and Elizabeth, for putting up with their very peculiar father who did not spend enough time at home with them. So thank you for you listening, and that's all we've got time for. Thank you.
We thank you, Professor Kosterlitz. Thank you for your talk, for a great talk, and thank you for accepting our invitation. We have already a question from Belita Coiler. Belita, you can speak out or you can write your question. You have to unmute your microphone first.
Hi, can you hear me?
Yes.
Very nice talk, very nice work, of course. I want to know a minor point. In the curves you showed the 1/q values. There's a second bump, there's a peak for the dissipation, right? And then there's a bump that the theory does not follow. Do you have a physical explanation for that peak? Why no peak?
Well, you mean the big peak? That's the dissipation peak. Now, of course, I only did the equilibrium statistical mechanics, and of course, which cannot address any dissipation. But the dissipation is purely in in the dynamical problem.
But
And
you have an interpretation for the high peak, and there's no interpretation for the low peak.
I'm sorry, I'm a bit stupid. Let's go back to that.
Yeah, this.
Oh, you mean the peak
Yeah,
at low temperatures?
because it seems to be a real peak. It's not.
Yeah, sure. But then that's not really in the theory.
Okay. No, I was just wondering.
This is below the transition, and you know, all sorts of things could actually be going on in the time dependence of things, which is simply, you know, not in the theory, because the theoretical problem concentrated on the major peaks, you know, the sharp dissipative peak, which was basically at the same point as where the superfluid density goes to plunges to zero.
Okay, thank you.
And you know, and so trying to describe what's going on in these minor peaks at low temperatures.
But it seems to be very clear. That's why I thought.
Sure. No, certainly. There's a lot of stuff going on which the theory does not even address.
Yeah. Okay. So there's no interpretation. Okay.
And I have no idea what it is, but it could be anything. I mean, you see, the transition. We always assume that the transition is described by, you know, long range, low frequency fluctuations. And therefore the theory only takes account of these excitations. It does not even think about any other excitations which are less prominent.
Okay.
Maybe one could explain that bump by a more detailed theory. I have no idea.
Okay, thank you. That's enough.
You're welcome.
Okay. Any more questions? I see that Enzo has unmuted his microphone. Enzo, do you have a question?
How do I do this thing? Can I just say here like this?
Yes.
Yeah. Okay. So I think Mike, you didn't have much time to say a lot about the two-dimensional melting, except at the end. But you only refer to this agreement for this melting thing, right? But there is, for the two-dimensional melting, there is also this two transitions. There is an intermediate phase.
Oh, sure. No, I mean,
and there is also, is there a good agreement for these two transitions as well in some experiment that you have time to mention probably?
Well, yeah, I was sort of running out of time. I mean, there certainly is, in the melting problem, there is the melting really has two things going on. There's the translational order, and this is destroyed by dislocations, but a crystal also has orientational order. And you can have orientational order in the absence of translational order. And so the orientational order is destroyed by excitations called disclinations, which are exactly analogous to vortices. And so really there is a reasonable theory of the melting will consider, at lower temperatures, we'll consider the dislocations. And then once the system is melted, you can argue that the interaction between the disclinations, which will survive, is exactly the same as the vortices in the superfluid, logarithmic. And so one can say that there's a transition at a temperature higher than the melting temperature, where the orientation order is destroyed. And so this would be the hexatic to isotropic fluid transition, because the melting the phase, if the dislocations unbind, then what this will do will destroy translational order, and the crystal will actually melt, but some of the orientational order will survive. And this phase is called the hexatic phase. And the hexatic phase is destroyed by the disclinations unbinding. And then there's a transition to an isotropic fluid. Now, I haven't been following this topic very much, but I believe that this intermediate hexatic phase has been seen in certain systems, and the theory is quite well verified experimentally. First of all, the melting, loss of translational order by unbinding of dislocations, followed by the loss of orientational order by the unbinding of disclinations. I think that this has been quite well verified.
Okay, we have a question from our YouTube viewers. First question is from Ricardo Lopes. Thank you for the nice presentation. I would like to ask if is the main influence, what is the main influence of external fields in this type of transition?
Well, the sort of the external fields are a little bit difficult, because what can you do? You could apply a uniform superfluid flow. And of course, this will mess things up somewhat, because if I assume let's say in the superfluid, if I assume my vortices tend to be stationary relative to the substrate, which is a very reasonable assumption, because the vortex core is a normal fluid, and this will tend to stick to the substrate. And so the superfluid will then flow past the vortices, unless they uncouple from the substrate. And so you could say that this external, you could apply some external flow to the system, and this will presumably act like a field. Now, I think that this has been analyzed. I can't remember the reference, and I think this is pretty well understood what happens there. In the case of a two-dimensional solid, you could apply, the sort of fields you could apply would be, a shear stress, or some uniform, compressional stress or something like that. And that would probably correspond to fields for the melting. And I'm sure that the phase transition will essentially go away in the presence of these fields. But I'm not sure.
All right. I don't see further questions. So is there any other question? So if not,
may I ask you one, please?
Sure, Angela.
So Professor, thank you for your very good talk. So my question is concerning all the number of proposal practical application of your theory. Which one are you looking for, especially that you would like to see in the future?
Okay, well, personally, I'm not terribly interested in applications, but that's just the way I am. Now, really, for the classical problem, there aren't that many. It's difficult to see what applications the theory will have because, directly, but the main reason why I got my share of the Nobel Prize for this was for the introduction of topology to physics, because the vortices are topological excitations and so are dislocations. So in that sense, Thalles and I were responsible for really the first introduction, the first time that topology was introduced to physics. But of course, when I was doing the work, I had no idea that we're doing something to do with topology, because I wouldn't have known a piece of topology if it had sat up and barked. And so, David Thalles, of course, he was a guy who knew everything about everything. And so he did say that actually what we're doing is we're looking at some topology. But of course, I had no idea what topology was, except that it was some obscure piece of mathematics. And, because as far as I was concerned, the only thing I was thinking about was the energetics of the system. Now, certainly, the argument that that a vortex, that these vortices can cause a transition from one topological sector to another, that's fairly clear, but the actual relevance of the discussing things in terms of topology seemed to me to just be introducing a piece of mathematics to describe what was sort of obvious. Now, but of course, it's become more important with the theory of the so-called topological insulators, where topology is really more important there. And so if it wasn't for the discovery of these topological insulators, I don't think that this work would have been, awarded a bit of a Nobel Prize. You see, actually, it was interesting because I was, needless to say, that when I heard that I'd got the Nobel Prize, I was, very, very pleased. And then later on, I heard how the money was going to be split up. And, so the way it was split up was that Duncan Haldane and I got a quarter each, and Thalles got a half. When I first heard this, I thought, hey, that's not fair. It should be a third each. Now, I mean, it's not to say I was, I was objecting to anything. I just wondered why there was this, this different division. And thinking about it a bit further, I realized that actually the Nobel Committee had been much smarter than I was, because the Nobel Prize was given for two things, really. It was the classical bit and the quantum mechanical bit. And I had only worked on the classical bit. Haldane only worked on the quantum mechanical part, but Thales had worked on both parts. So it seemed, therefore, when I thought that way, the division was much more reasonable, right? Because half the prize was given for the classical work on classical systems, and half the prize was given for the application of topology to quantum mechanical systems. And since there were 4 people involved, 2 people in each field, the prize was split 4 ways. But of course, you can't have 4 people sharing a Nobel Prize because the maximum is 3. But things worked out very well because one of the people in both fields was the same person called David Thales. And so he got 2 quarters of the prize, and Haldane and I got a quarter each. So that was very fair.
All right. We have a question from Mauricio Coutinho. Mauricio. You have to unmute your microphone.
Hello, Mike. Can you hear me? It's Mauricio Coutinho.
Yeah, hi, yeah, I can hear you.
Okay. I have just one question related to a recent work on physical review letters by Suitable and co-authors about fingerprint of the universal spin stiffness jump at the Kosterlitz transition. But they involve a direct measurement by the array involving charge current cross correlations in a metal magnetic hybrid structure. And so by measuring some flowing of current and measuring some current out of the magnetic part of the system, they can achieve a way to measure the direct value of the stiffness constant that you described so well by statistical mechanics. So have you had some contact with this work by Alberto?
No, I haven't.
Ashley Suitable, you probably know him.
Yeah, I know. I mean, I know him. He was actually Tony Houghton's student in Birmingham.
I see.
So I mean, I knew him pretty well.
Yeah, it's an interesting setup of transport properties, but they can isolate the measurement of the stiffness constant at
Right.
the jump of it up at the Kosterlitz transition. So it was just published this month in Physical Roulette, the first week of December. Okay, you should have some contact with this prediction to see if it's a good way to measure. They say it's a direct measurement of the stiffness constant. And I'd like to congratulate you, my your Nobel Prize winner, and for our opportunity to be just when you did your work. We were both at Cornell. It was a great time, and we saw each other again in Brazil, in Recife, during the StatPhys conference, and that's it.
Yeah, that was a fun period of my life when I was a postdoc, no responsibilities. I could do what I liked, and had time to think, and I'd just explore whatever problem caught my fancy. It was a wonderful time, and I just got very lucky.
Yes.
Because at the time I had no idea that the theoretical developments would have such such a an impact and be applied to so many different systems. And no idea that would happen. And so
Okay.
it's had a fun time.
Yes. Okay, good luck.
Thank you.
Thank you, Mauricio. I don't see any more questions, so I would like
Right.
to ask everyone to. Is there a question? I would
Well, I
like
don't
to
know
ask
how,
everyone
yeah. Sorry,
to open.
can I ask you another question because I don't know how to proceed with this
Go ahead,
chart thing.
Andrew, go ahead.
I will take the opportunity and ask a question that I probably never I had time to actually ask Mike all those questions during the time I was doing PhD, but I never asked it. But this one, I would like the opportunity now. There is this unpublished work by Richard Feynman on the melting, on the ideas of the melting. Were you and David Thomas aware of this work when you developed the theory?
No. I heard the story that, Feynman was very pleased with what he cooked up, and then very upset when he was told that a couple of guys in Britain and England had worked out the theory in some detail. So it's very nice to know that to be in the same company as someone like Feynman.
All right, so I would like then everyone to open their microphones and let's give a hand of applause to our speaker, Professor Litz. Thank you very much.
Thank you.
And well, I like also to wish everyone Merry Christmas and a happy 2021. And we will resume our webinar series on February. So thank you for coming, and see you on February.
Bye, Mike. Bye, everyone.
Goodbye.
Enzo, are you the organizer of this series, or what?
No, I'm
Yes,
I cannot.
Professor.
Yeah, I cannot organize even my life, so it was not me.
We are the Commission on Condensed Matter Physics of the Brazilian Physical Society, and we are organizing this webinar series every 2 weeks.
2 weeks?
Every 2 weeks, yes.
Wow, that's a lot of work. Of course, it's now cheap because you don't have to pay airfares and stuff like that.
Yeah. Well,
That's right. Yeah.
Congratulate everyone, including